Inferential statistics, the subject of most of this class, is really about one thing. Is the mean of a sample what we expect it to be? In order to find an answer to this question, we need to take into account the amount of variability in the data set that produced that mean. If there's a lot of variability in a data set, then the mean we calculate doesn't provide a very good summary of the scores. On the other hand, if there's only a little bit of variation in a data set, then the mean probably does provide a good summary. In this video, we'll look at a few different ways of measuring variability and how to compute them. The range is the most basic measure of variability. It's simply the result of subtracting the lowest score from the highest score. Here's the final exam data we've been looking at. It's probably easiest to sort the data first, though strictly speaking that's not necessary. If I sort it, however, it's easiest to see the lowest and highest scores. A simple subtraction gives us the range. In this case, 93 minus 28 equals 65, so the range would be 65. The problem with the range is that it includes these outlying scores of 28 and 93. They don't really tell you very much about what's going on with most of the values. You know, because this is an exam, that the range of possible scores is 0 to 100. If you know that, then knowing that the actual range of scores was 28 to 93 doesn't really add that much more information. That brings us to another useful measure of variation called the interquartile range. The interquartile range is simply the difference between the value or score at the first quartile and the value or score at the third quartile. Let's take a look at a number line to see how these work. The first quartile is the value at the 25th percentile. It would be about here. The value at the third quartile would be about here. The shaded area in between is the interquartile range. You might want to pause the video to take a look at this more closely. Let's work on a problem now. This table shows the number of births per 1,000 population for 40 countries. Finding the interquartile range involves finding the score at the first quartile, Q1, and subtracting it from the score at the third quartile, Q3. The first step is to sort the data set. In this problem, as you can see, the data is already sorted, but it's sorted from highest to lowest score. We can still work with this. We'll just have to remember to count up from the lowest to the highest score. Here are the steps. Since the data is already sorted, we'll start at step 3. To find the score at the first quartile, we multiply the number of scores in the data set by 0.25. We'll call this the position of Q1, or PQ1 as I've written it out here. In this case, there are 40 scores, so PQ1 equals 40 times 0.25. 40 times 0.25 equals 10. So far, so good. We know that the score we're looking for will be the 10th one. We find the 10th case by counting up from the lowest score, and in this example, that score is 13. We repeat the process for the third quartile. Here we have 40, again the number of cases, times 0.75. This equals 30. We've got these cases numbered in the table, so the 30th case would be this one here. The score here is 35. If we subtract 13 from 35, we get 22. So for this data set, the interquartile range is 22. A box plot provides a great way of viewing a data set because it allows you to examine a number of key statistics all at once. It's what you would call a data-rich graph. Let's take a look at the parts of a box plot. The line in the center of the plot is the median value. Excel also gives you the mean value. It's the little x here. In this example, the mean and the median are nearly the same. The outer edges of the box provide the first and third quartiles. The whiskers show the minimum and maximum values. There's one exception to this. It's worth noting. If there are any values greater than 1.5 times the size of the interquartile range, then the whisker is drawn at a point 1.5 IQR units, 1.5 interquartile range units above the top edge of the box, and any extreme scores are plotted as a dot or asterisk above that top whisker. The same is true for any values that are less than 1.5 IQR units below the bottom edge of the box. In this data set, there aren't any extreme scores. The real beauty of a box plot is that it allows you to see all this information for several data sets all at once. Here we have the data from the final exam of 2 statistics classes. While the means and medians are nearly identical, Class 2 has a good deal less variability than Class 1. This raises all kinds of interesting questions. Were the students in Class 2 more homogeneous? Were the 2 classes organized differently? You can plot as many data sets as you want on a box plot and make these kinds of comparisons with just a glance at the plot. I use them a lot in my work, and I'm very happy that Microsoft has finally included them in Excel. The range and the interquartile range are essentially qualitative measures of variation, but they lack precision. For that, we need another measure. I've defined something here I'm calling the average deviation. As you can see, if we simply add up all the scores and divide by the number of scores, we're going to get a 0. This is always going to be the case. It's in the nature of what a mean is. The mean represents a balance point, and as such, you can't use it to assess variation. We're on the right track here, though. The problem is these negative numbers. There are a couple of ways to get rid of them, but the way it's done is simply to square all the differences. Remember that a positive number times a positive number gives a positive number, and a negative times a negative gives a positive as well. If we multiply these values by themselves, if we square them, we're always going to get a positive number. In this example, negative 3 squared is positive 9, 0 squared is 0, etc. When we sum these up, we get 20. We call this the sum of squares, SS for short. As the equation shows, we divide this sum of squares by n, the total number of cases. There are 5 data points, so we divide 20 by 5 and get a value of 4. Unfortunately, this value is not actually the standard deviation. It's another important statistic called the variance. What's the problem? Well, when we square all the differences, we not only get rid of the negative numbers, we also greatly expand the differences. Mathematically, it's not a problem, but it's misleading. It makes it seem as if the differences are larger than they actually are. So how do we address this? Well, we simply take the square root of the variance. You should note that the standard deviation for data from a population is denoted with the Greek letter sigma. Let's look at both the standard deviation and the variance together. As you can see, the symbol for variance is simply sigma squared. There's just one more thing to point out. Here again is our formula for standard deviation. Because samples typically have less variation than the populations from which they're drawn, we have to introduce a small correction. Instead of dividing the sum of squares by n, we divide by n minus 1. Also note that we've gone from Greek letters to Arabic letters when we're working with a sample. Let's take a look now at a problem. Here's a summation table along with a formula for standard deviation of a sample. You definitely don't want to forget that this is for a sample. If you do, you won't get the right answer. Step 1 is simply to subtract the mean from each score. So for the first score, we have 85 minus 77, which equals 8. Now we have to square each one of these scores. 8 squared is 64, and again, here's the result for all of the values. You can see in the last row that the sum of squares is 3,338. That allows us to simplify the first equation. So we have n equal to 17, and since we have a sample, we need to subtract 1 from that value, and that gives us this. From there, it's a simple matter to solve for s and to determine the standard deviation. I hope that you found this presentation helpful.